our warm-up problem. And now we're in the part of the course where we don't have to use lots of words. These aren't story problems. We're just like, boom, integral. Okay, so here we have integral 1 to square root of 3, 6th log of 1 plus t squared over t squared dt. And on a side note, this comes from an old final, this problem. The final was an indefinite integral, but essentially that's where the source is. So, we're already up to like exam level problems here. All right, so we have a bunch of options. I won't read them out, A, B, C, D, or E. Do we have an answer? Has someone cracked the code? I see one hand, yes?
Option E.
Option E?
Yeah.
Are you sure?
Yeah.
Okay, good. You're correct. All right. Now, I like this problem, and you can quickly tell in almost an instant, you're like, aha, I see an arctangent. Yes. Yes, that definitely sways me. Now, what's our technique? What's our tool? We can kind of cheat a little bit here because we know what we talked about last time, and so that helps inform us. Now, unfortunately, as we go into the exam, one of our challenges is going to be how do we recognize what tool to use? So that's one of the things you have to think about over the next few weeks. How do I recognize when to use a tool? So here we're going to be doing some integration by parts because that's what we just talked about. Now, one of the things that suggest integration by parts is you have multiple things. And there's one piece of advice. How do you find the part that you differentiate? How do you find the part that you integrate? Because that's oftentimes the challenge. It's like, I have the formula, great. But how do I know which part is which? And so one thing I often do, I ask myself a question, is when I have an integration by parts problem, I say, well, what don't I want to integrate? If there's something inside that integral that says, I don't want to integrate that, then I say, okay, great, then I won't integrate it. I'll differentiate it. And so, in particular, logs. I don't want to try to integrate that. I don't know how to integrate that. So I say, okay, great. I know that's going to be my part I differentiate. That's the u. Well, we need to figure out what the du is. Take a derivative of log. Derivatives of logs are pretty straightforward. You have a fraction. Whatever's inside the log goes downstairs. The 1 plus t squared is in your denominator. The derivative of that goes upstairs. Derivative of 1 plus t squared is 2t. So then it must be that whatever's left over, which is 6t to the negative 2 dt, that's your dv. And we can integrate that, negative 6t to the negative 1. And t to the negative 1 means divide by t. So then we have our uv. That's our first term. It's a definite integral, so we'll need to evaluate from 1 to root 3. And then we have our v du. And here we have the fun part where the t's end up canceling, so we get a 1 over 1 plus t squared. Well, we evaluate. That's not very exciting, but we work it through. One thing to note is that 4 and 2 are very close. So log of 4 and log of 2, we can combine them together by saying, well, 4 is 2 squared. And one of the properties of logs is you can bring that exponent down. So log of 4 is the same as 2 log of 2. So that's what lets us put the things together. And then this is one of our basic integrals, which is arctangent, which we can evaluate. And it turns out that if you look at our formula sheet, we can figure out what arctangent of root 3 is, and we can figure out what arctangent of 1 is. We just look in the row for tangent and say, where does 1 and root 3 show up? So arctangent of root 3 is pi over 3, and arctangent of 1 is pi over 4. We clean it all up, and we get our answer. All right. So that's our fun warm-up problem. Any questions?
What's the meaning of life?
What's the meaning of life? Well, I hear that the ultimate answer to life is 42. The only problem is nobody knows the ultimate question. So we'll work on that. All right, thought for today. The value of identity, of course, is that so often with it comes purpose. Now, this, of course, can have multiple interpretations. And part of it is it's important to know who you are. And it's not a great life to not know who you are and to go through life sort of numb and mindlessly. You should know who you are. You should know what your identity is. And that should inform you. And that should encourage you and inspire you. And, of course, it will change. It will grow. You'll learn new things about yourself. And that's wonderful. Now, as an example, I personally identify as somebody with a beard. But for 6 years of my education, I was at a school where I was not allowed to have a beard. It was mandated. There shall not be beards here. I had to suppress my bearded self and live a lie. But now I can finally be free. I can grow my beard. So,
you have an amazing beard.
well, I don't know about that, but now there's, of course, another meaning, which is today we're talking about trigonometry, trig identities. And each trig identity doesn't just happen in a vacuum. It has a reason. It has a use. And so we're going to be working a lot with our identities today. So what are the goals for today? Well, we're going to do a little more practice with integration by parts. And looking ahead to next time, on our next lecture, it's sort of a practice day. So in terms of content, there's not as much content in this portion of the course, which means we get to do lots of practice. And so practice will continue on Friday. Okay, but the other thing is we're going to work with trigonometric integrals. Now, in terms of the formula sheet, we're not learning anything new, but we have this portion of the formula sheet, which is loaded with identities, and of course we have our trigonometric integrals. So we do have some blast from the past, so to speak. So that's where we're going. So let's go and do a few examples. And this just seems obligatory at this point. Find the integral 0 to 1 arctangent of x dx. Now, is arctangent one of our basic functions, something that we know how to integrate? In other words, is it on our list of 10 functions who's like, yes, we know how to integrate arctangent? No. What can we do with arctangent, though? We can differentiate arctangents. So we're like, aha, here's something I don't want to integrate because I don't know how, but I do know how to differentiate it. So there's a great aha moment that says, let's do it by parts, where we say, I am going to think of this as parts, and there's my u. But now the question, where is the dv? Because integration by parts says there's two things multiplying together. So if u is arctangent of x, what's dv? Yeah, essentially it's everything that's left, and it can just be the dx. It's okay to just have your dv be dx. That's perfectly allowed. And this shows up, for example, when you have things like integral of a log or integral of arctangent. All right, so if dv equals dx, what does v equal? X. All right, and then if u is arctangent of x, what is du? 1 over 1 plus x squared dx. All right, so there we go. We have our problem started. So our formula, uv, x, arctangent of x, and then we check to see if it's a definite or indefinite integral. So it's a definite integral, so we're going to need to do some evaluation, minus the integral v du. So that's x over 1 plus x squared dx, and 0, 1. There's no changing of the bounds here. This is not substitution. The same bounds carry through. Well, let's do the first piece, our evaluation here. Well, the good news is when we plug in 0, what happens? We get 0. It's hard to recover from multiplying by 0. So we have 1 times arctangent of 1. Arctangent of 1, also known as? Pi over 4. Nice. Okay. So, we've updated our problem. Our original problem was we wanted to integrate arctangent of x. We said, I don't know how to do it. Integration by parts says, okay, instead of integrating arctangent of x, you can integrate this expression, x over 1 plus x squared. So now we say, okay, can we integrate x over 1 plus x squared? And if so, how do we do it? Substitution, I heard. Yes, yes. We don't have to do parts again. Every time we have a new integral, we always look at it with fresh eyes and say, what does this integral present to us? All right. So if we do substitution, what's our substitution? 1 plus x squared. And what will du be? 2x dx. But we'll use our sophisticated marker technology to move that across. So we say a half du is x dx. Now we still have that pi over 4 from the first piece. We're still subtracting. Now, this is a substitution. Our bounds do change. So our old bounds were from 0 to 1. What will our new bounds be? 1 to 2. So you plug in x equals 0, u equals 1. Plug in x equals 1, u equals 2. Then we have our x dx becomes a 1/2 du. So that's our x dx becomes 1/2 du. And this 1 plus x squared downstairs becomes a 1 over u. Do we know the integral of 1 over u? Yeah, it's on our sheet. It's things we should know. So it's natural log of u. Evaluate from 1 to 2. Well, let's plug in. When you plug in your 2, you get log 2. What happens when we plug in 1? What's log of 1? 0. Yeah, it's good to know these things. Log of 1 is 0, so we don't need to write it down. And there we go. Now the pi is not surprising. The log might be, but that's okay. We follow the process. And wherever it goes, that's where we'll go. All right, any questions? Good. In that case, I think we can do one more. Find the integral of cosine theta log secant theta plus tangent theta. Okay. This feels like integration by parts. There's things multiplying, and there's one thing that I really don't want to integrate. That's right, that cosine. Oh, wait, no, that's okay. I'm okay with that one. That log of secant plus tangent is like, ugh. However, log secant plus tangent should ring bells. Have we ever seen log secant plus tangent before? And where have we seen it? The integral of secant is log of secant plus tangent. Now that tells us if we take the derivative of log secant plus tangent, what does it become? Becomes secant. If the integral of secant is log of secant plus tangent, then the derivative of log secant plus tangent is secant. So you say, this thing which looks terrible to integrate is really clean to differentiate. So that says this is our u. And we'll just make a note here. We've already talked about it. The derivative is secant. Well, what does that leave for our dv? Well, it's whatever's left over. So we have that dv is cosine theta d theta. What's the integral of cosine theta? sine. Okay, so we have our integration by parts set up. We figured out what our parts are. So we're going to take uv. And so I'll put the sine in front. Sine theta log secant theta plus tangent theta. And this is an indefinite integral, so we're not doing any evaluations. Subtract the integral of v du. Sine theta secant theta d theta. All right, so this at least feels better. We switched our integral problem. We still have an integral problem. So when you do integration by parts, you're just saying, I'm trading one integral for another. And now, the original integral looked messy because there was a log. Our new integral just has trig. And it feels like we have a chance, a real chance to figure it out. But how? What do we do? Okay, so how do you integrate sine theta secant theta? What's that? It's tangent. How do you get tangent here? So certainly sine is sine. What's another way to write secant? 1 over cosine. And then this is really sine over cosine, which means it's tangent. Okay, so this is a little bit of using trig knowledge, like trig facts. So we can rewrite things. And that's one of the nice things about trig, is that there's lots of ways to rewrite things. On the other hand, one of the bad things about trig is that there's lots of ways to rewrite things. And so it's a double-edged sword. There's pros and cons. And the pro is, of course, there's great flexibility. But the con is, which way do you go? Do we know the integral of tangent? Is that on our list of things we know how to integrate? Integral of tangent. It's natural log of secant. All right, is this our answer?
No.
What? But we worked so hard and I already put a box. Darn it.
Plus C.
Oh, plus C. Oh, good. I left enough space. Phew. Crisis averted. All right. Good. Good. All right, there we go. Okay, so any questions on this one? Are we good? Of course. All right. Like I said, don't worry. More practice is coming next time. All right, so that brings us to today's new topic, trigonometric integrals. So we're integrating things with basically trig functions. And how do we do it? Well, first thing is, there's a lot of trig identities out there. Well, there are 6 in particular that we often use. So the 6 are what you could call the Pythagorean identities. And this basically boils down to the fact that in a right triangle, a squared plus b squared equals c squared, you work it out in terms of trigonometry. You can say, well, sine squared plus cosine squared equals 1. Or tangent squared plus 1 equals secant squared. Now, there is another one that says 1 plus cotangent squared equals cosecant squared, but we tend to avoid the co-ones. So, Pythagorean, there's double angle identities. Sine of 2 theta is 2 sine theta cosine theta. Cosine 2 theta is cosine squared minus sine squared. And then there's order reduction or power reduction, which says, if I have cosine squared or sine squared, I can rewrite it. So cosine squared is a half 1 plus cosine of 2 theta. Sine squared is a half 1 minus cosine 2 theta. So you'll notice a few things. One is on the insides, you have theta here, but you have 2 theta over here. So be careful. That's a common mistake people forget to do, including me. So I've made that mistake so often, I try to remind myself every time I do this. But the real key to observe is you say, you start with a square, And then you got to something which didn't need to be squared. In other words, it became simpler. And that's our goal. Our goal with using trig identities is to try to simplify what we're integrating. So we can start with very complicated expressions and get down to things which are very simple. All right, so what's our strategy? Well, as I already said, try to get a simple expression. But a common thing that will also happen is that we are going to take some integral that involves trigonometry and rewrite it by a substitution in some appropriate way so that it becomes an algebra type integral. So it becomes an integral of a polynomial. So in other words, we're going to talk about this idea of taking trig integrals and turning them into algebra integrals by appropriate substitution. Now I might say, well, that's cool. Can you ever go the other way around? Can you ever go this direction? And this is, yes, you can. This is coming soon, but not today. It's going to be a fun topic. One of everybody's favorite topics of Calc 2. So, all right. Lots of comments. Don't worry. We'll also have time for problems. A couple of notes. Make sure your insides match. So if you have a problem where you have some part of it says theta and some other part of it says 2 theta, you say, okay, before I do anything else, I need to make sure all my inputs look the same. So you really need to have the same apples, right? You don't want like apples and oranges. You want apples. So make sure your insides match. And if they don't match, look for trig identities that let you do that. The Pythagorean identities, so I'm going to pull these back up here. These two, one of the most common ways that we use these is to say, hey, if I have a sine squared, I can make it look like a cosine squared. Because sine squared plus cosine squared equals 1. So I can say, well, sine squared I can replace with 1 minus cosine squared. So I can swap sine squareds and cosine squareds. Same idea, I can swap tangent squareds with secant squareds. Now, it's not a one-to-one, there's a little bit of extra thing, but we still have that sort of flexibility. And so we use that frequently, this idea that like, oh, if I could only make my sines into cosines, and like, aha, we can, as long as there's an even number. Right? As long as you have even powers, you can make that trade. And that's a trade that we'll often be willing to make. So be open to sort of this idea. It's like, what if I could swap the sines for cosines? What if I could swap secants for tangents? And so this is a very useful identity for doing that. When in doubt, put everything in terms of sine and cosine. So in particular, if you have something involving, say, sines and tangents or cosines and tangents, sort of this sort of mixed bag. Put everything in terms of sine and cosine and work with it from there. We kind of alluded to this before. Some problems do have multiple approaches. So you can say, well, I could use this trig identity and then go down this route and I can get an integral. Or I could use this trig identity and go down a different route and I'll get this answer over here. And so as a consequence, you may end up with two answers that look very different. But they only look different. They're equivalent in some sense. Now, when we say they're equivalent, what does that mean for integration? They're the same up to a plus c. So the two sides are equal up to a plus c. All right, so we're only going to do a few special cases, but this should give you enough to whet your appetite. And the ones that we talk about are the ones that we tend to test on. Okay, so the first case, what happens if I have an integral of sines and cosines? So sine to a power, cosine to a power. Sine to the power p, cosine to the power q. Well, there's two cases. The first case is if one of them is odd, that's great news. So if either P or Q is odd, let's suppose it's P. So there's an odd number of signs. What we can do then is take one of those signs and pull it to the end. And we say, okay, now there's an even number of signs left and a bunch of cosines. I don't know how many cosines, it doesn't matter. What can I do with an even number of signs? Is there anything that we can do with an even number of signs?
Square it to a certain degree.
Well, that's not what I'm thinking of. Sorry, what? Oh, we could trade with what? We can trade them with cosines. So if we have an even number of signs, so sine to an even power, I can swap it out and say, aha, oh, it becomes a bunch of cosines. And then what you end up with is something that looks like this. It's a bunch of stuff with cosines and then a single sign. Now, why is that nice? Because now there's a clean substitution. U equals cosine, and then du is negative sine. And so it becomes an algebra problem. Similarly, if you have an odd number of cosines, you can pull a cosine off, rewrite everything in terms of sine, and again, we can do a substitution. So if one of them is odd, pull the odd part off, rewrite everything that's left in terms of the other, and off to the races after a substitution. No big surprise. But what if they're both even? Well, if they're both even, then we start doing our order reduction, or our power reduction. Say, okay, let's make it a simpler problem. And we have 3 order reduction. Now you might say, wait a second, Steve. You said 2 before, but there's a third one that we don't often call order reduction, which comes from the double angle formula. So that fact that sine 2 theta is 2 cosine theta sine theta allows you to say, aha, cosine theta times sine theta is half sine 2 theta. And I strongly encourage you to use this last one as much as you can. Why do I like this last one? Well, look at the other two in comparison. What do the other two have that this one doesn't? The plus or the minus. That means the more pluses and minuses you have, the more expanding you have to do. And that says, uh-oh, algebra. And it seems to be the case. People don't like algebra. And so if we can minimize it, we have a chance to maximize our scores. And we like high scores. All right, so let's do some examples. Find the integral from 0 to pi over 4 of 30 times sine to the 5th theta d theta. All right, what can we do? Any suggestions? Well, we do have an odd power. So, what's our strategy? If we have an odd power, what do? We pull one of our odd powers to the end. So, we'll do this in slow motion. And our idea here is that we are going to think of this as becoming our du. That's our goal. That's going to become our du. But we say, okay, so that says if that's our du, we need to have everything else in terms of cosine. So there needs to be a trade, an exchange. We say, well, good news for us, yay us, because this is an even power. I'll think of this as sine squared. So that's why we say we like even powers. Now we trade. What does sine squared become?
1/2 1 plus cosine.
Sine squared becomes? 1 minus cosine squared. So we're doing our trade here. This is not power reduction. It's trading sines and cosines. So now we say, great. We're in a good state. Because what we have is we have the derivative of cosine here. And all of this is stuff with cosine. Now, it's not, I know it's not technically the derivative of cosine, but spiritually it is. Okay, so our great aha, we're going to say u equals cosine. What is du? Negative sine. The derivative of cosine is negative sine. And then I can just say, well, I'll move the minus across. So minus du is sine theta d theta. Okay, so we can update. Integral. The 30 becomes? Yes, it's a number. We don't do anything. 1 minus cosine squared squared. 1 minus u squared squared. The sine theta d theta. Negative du. And the bounds. The bounds, the bounds. We must remember the bounds. All right. Well, we were going from 0 to pi over 4, but we've got to update. What is cosine 0? 1. What's cosine pi over 4? Root 2 over 2. We have the formula sheet in case we forget. All right. Well, this is going to be a suspiciously probably not pleasant answer, but that's okay. What's our next step here? Suppose you had this integral. We've turned our trigonometry integral into an algebra integral. What tool of algebra do we need? Expansion. We got a FOIL. And the other thing I'm going to do is I'm going to use the minus to change the order of the bounds. Because remember, if you flip the bounds, you change the sign. And this feels a little bit strange because 1 is actually bigger than root 2 over 2. So it feels more proper to write root 2 over 2 to 1. Then we're going to have 30. And if you FOIL this, you get 1 minus 2u squared plus u to the 4th. All right. Well, we are getting closer to the end. Okay. So, let's integrate. Equals, we have a 30. What's this integral become? U minus 2/3 u cubed plus 1/5 u to the 5th. Evaluate from root 2 over 2 to 1. Now, if you multiply the 30 through, I mean, it's suspicious that we have a 30 here. We get 30u minus 20u cubed plus 6u to the 5th. Evaluate from root 2 over 2 to 1. Okay, so we plug in 1. 1 is pretty quick to plug in. What do you get when you plug in 1? Well, you just get the coefficients, 30 minus 20 plus 6, which is 16. So we like 1. I mean, we prefer 0, but we like 1. When we plug in root 2 over 2, no, come on, we can do it, we can do it. All right, so 30 times root 2 over 2, well, that's 30 root 2 over 2. Minus 20 root 2 over 2 cubed plus 6 root 2 over 2 to the 5th, and that is all being subtracted. Well, we go through term by term. The first part, 30 over 2 makes 15 root 2. Okay, so let's, on the next part, we have 2 cubed is 8. What about root 2 cubed? What does that make? 2 times square root of 2. Because you can think of it as a root 2 times a root 2 times a root 2. 2 of those root 2's combined to make a 2. All right, let's see. We have 40 over 8, that's 5. So that's a 5 root 2. Okay, how about this last part? We have 6, 2 to the 5th, 32. What about root 2 to the 5th? What would that be? Become 4 root 2. Well, this was not carried out quite as good as I would have liked, but what can we do? We can do a little bit of cancellation. We can cancel 4 and 8. Here we have 3 and 4, so this is really a 3/4 root 2. So I don't know why I'm putting so much energy into this, but okay. 15 minus 5 root 2, that's 10 root 2, that's 40 root 2 over 4, plus 3 root 2 over 4 makes 43 root 2 over 4, giving us our final answer of 16 subtract 43 root 2 over 4. Ta-da!
Lovely.
There we go. There we go. Yeah, a little bit of messy algebra at the end, but that's all right. That's just a couple of points. All right. Well, let's try a different one. Sine squared cosine to the 4th. All right. What do we have here? We look at our powers. Square and 4. So, they're both even. So what's our mindset now?
Trade.
It's not trading, it's power reduction, order reduction. We want to reduce our powers. So we have our 3 identities ready to go. We have that sine squared is 1/2, 1 minus cosine, double the angle. Cosine squared, I'm just putting this down for reference. 1 plus cosine, double the angle. And of course, a cosine times a sine, which by the way, true story, same as sine times cosine, is 1/2 sine of double the angle. So those are the 3. Once we see they're both even power, we say, aha, here's our little collection of things we're going to use. Now, as a reminder, I strongly encourage you to use this last one as much as possible. It will greatly simplify your computation. So let's imagine we're trying to be nice to ourselves, because we should be nice to ourselves. We're good people. We deserve good things in our life. So, with that being said, I say, well, I'm going to think of this in the following. I'm going to put as many sines and cosines together as I can. So, how many sines and cosines can I put together? I can put 2 of them together. So I think this says sine t cosine t squared, and then I have 2 cosines left. Well, sine t cosine t becomes 1/2 sine 2t. Now that's inside the square. The cosine squared, that's 1/2 1 plus cosine 2t. All right, so updating, what do we have? Well, when we square this, we're going to have a 1/2 squared. There's a 1/2 here. I'm going to go ahead and put all those together and say we have a 1/8 sine squared of 2t, 1 plus cosine of 2t. All right. Now, what can we do? We can distribute, expand out, this frequently happens, perfectly reasonable to do where we're allowed to do it. Very unreasonable to do when we're not allowed to do it. So you have 1/8 sine squared of 2t plus 1/8 sine squared of 2t cosine 2t dt. Okay, now look at the first term, because notice here we have a plus. What does a plus say you can do? When you see a plus in integral, it tells us what? This is a good plus. It tells us we can really think of this as two integrals. So you have 1/8 sine squared 2t dt, and you have a 1/8 sine squared 2t cosine 2t dt. Take advantage of linearity. Pull things apart. Occasionally you take advantage of linearity by pushing things together. And the moral here is you might want to do different things to different parts of the integral. So that's why it's convenient to pull them apart. Because looking at sine squared of 2t, what would we like to do? Is there anything convenient for us to do with sine squared? Anything at all? Anything? I hear a yes. What is it? Oh yeah, we can still do reduction. We're still allowed to do it multiple times. But look at this second integral, sine squared 2t cosine 2t. What would we want to do in this integral? Look at the powers. An even power, an odd power. We're like, nice. This is our preferred state. What would you do here in this integral? It's a u substitution integral. Because if you have the derivative of sine is cosine, if u equals sine 2t, du is cosine 2t. So you're going to do different things to the different parts. What? Why? This is a very curious. My screen on my computer just said, I'm giving it a thumbs down. No, I give this a thumbs up. I think this is great. All right. So, first integral, power reduction. So we have a 1/8, 1/2 sine squared 2t. Sine squared 2t, we have the 1/2, 1 minus cosine of, very dramatic here, 4t. Right? I warned you, this is where I make mistakes. Why is there a 4? Because you double what you started with. We already had a 2, you double 2, you get 4. Okay. Plus. Now, here, we'll work this out in a second. Well, u equals sine. du is 2 cosine 2t dt, or if you like, 1/2 du is cosine 2t dt. So what do we end up with? We have a 1/8 u squared, because there's our u squared. Then we have a 1/2 du. Okay, so from the first integral, we have 1 over 16. The integral of 1? T. The integral of cosine 4t. The integral of cosine is sine. There's a little bit of a gap here, suspicious. 1 over 4. Plus, well, we have 1/16, the integral of u squared. One-third u cubed. Is this our answer? No! You've learned that whenever I ask if that's the answer, it's like, no, Steve never gives us the answer. He makes us work for it. 1 over 16t. I'll go ahead and just distribute this 1 over 16. Minus 1 over 64 sine of 4t plus 1 over 48. We need to get back in terms of where we started. U was sine, so that makes a sine cubed of 2t. And that is our answer. All right. So one last idea, and I'll just give you a spoiler that when we start next time, your multiple choice will come off of this idea. So if you ever see things with 1 plus or minus cosine, 1 plus or minus sine, or secant theta plus or minus 1, use conjugation to help get you to something like 1 plus or minus cosine squared, 1 plus or minus sine squared, or secant squared plus or minus 1 to help you rewrite. This is especially useful inside a square root or inside a denominator.